Dear students, let us continue our discussion on training of neural networks. We have discussed about the role of activation function, how the activation function, which kind of activation function should are better for effective training of neural networks. We also have seen the pre-processing aspects of the input features to the neural network. We will discuss specifically how the weights has to be initialized for effective training. We have seen that even while discussing about pre-processing steps, when the data cloud and the weight initialization are completely at different locations, then the weight update doesn't happen, and it will give a serious limitation on the learning of neural networks. So now let's see how the weight initialization is more effective to make to combat such issues and to make the weight initialization initial weights somewhat overlapping with the data cloud as well. So just to start with, if we start with all weight elements to be 0, all weights to 0, and then initialize with the we all, then what's the effect? As we can see, all x1 d whatever we give, all will be multiplied with zeros, and the output itself is 0. Okay, so that's not very effective way of initialization. So this is completely ruled out. Then next option is the weight, all weights wji and wjk. So if we consider that wji are the weights here and wjk are weights here, okay, if we consider both are all constant, so in such case what will happen? So if these are all constant, so as we can see here, the output, say if we consider y here and o here, okay, so the y is equal to f of double transpose x plus b. Okay, and assume that b is also equal to w, and w, all w1 wd all are equal. Okay, the w vector has all initialized with constant weights w. Okay, and then this w transpose x essentially is equal to w1 x1 plus w2 x2 and so on, right? So this essentially boils down to w into x1 plus x2 plus and so on up to xd, okay, plus b. And if you just neglect this for time being, then this essentially w can be taken out itself, and this is a constant, this is in turn a constant. So the y1, y2 and y3, y4, okay, each of the neurons, this term essentially is same, right? So it's y1 is equal to y2 is equal to y3 and so on, yh. At all hidden neurons will have the same output. See, when the same output comes from each of them, so they're all y we can consider, and then essentially these are all w's. So the output here also o1, o2, they're all same. Okay, even though the targets t1 and t2 may be different, okay, but they will be same for sample 1, okay, for sample 1 and sample 2 and so on. For each of the sample, the same delta w's will happen, delta o will happen, and that implies same delta net, okay, and then same delta w. Initially w's are same, okay, and then subsequently delta w is same, because as you can see here, the output set of each of the hidden neurons are same because this term is constant, okay, and since outputs are same, the errors are same, and then the weight updates are also same. So in that case, no learning happens. So if w is constantly initialized, then this implies that no learning happens in the neural network. So this is also not a good procedure. Then what's the suitable procedure for that? Okay, all our weights are all duplicate. Okay, so wji is equal to wkj is equal to w, imply in fact delta wji is equal to delta wkj, okay, is equal to delta w, same. Okay, So it's effectively, it's of not a good strategy for initialization. Then what's the good strategy? We can initialize with random weights. Okay, and then uniform random weights is one procedure, or Gaussian random weights is other procedure with zero mean and small standard deviation. See, when we keep the standard deviation small, okay, so one issue that you can consider is, say if you have a network like this, okay, if we have smaller network, it is fine. So they will learn effectively even with, if we initialize with small random weights. But if we have a deeper network, okay, so in such case, what will happen? See, the activation function, if we use sigmoid activation function, okay, so this the output of this will be in the range, say these are all W's. So W transpose X, usually X is also normalized. Okay, being the values are all less than 1, and these are also less than 1, or all less than 1, and then W transpose X will also be effectively will not be much higher, okay, close to 1 or less than 1. It depends upon how small W's are. This will be even smaller. If this is by chance, if this is very small and this is also small, okay, then what may happen? These W's in turn will make further smaller. If W is smaller, this will be multiplied at several times while we are getting the final value. So O essentially is equal to F3 times W transpose, okay, into F2 W transpose F W transpose X. Okay, B I have eliminated, I have not considered here. So hope this you understand this notation, what I'm writing here. Okay, essentially what it takes several layers. At each of the layer, what we are doing, we are using an activation function and a matrix of weights. Okay, and this W is smaller. That essentially also multiplies for several times, and hence the outputs will be smaller. So here it will be very small. Here it is very, very small. And this will be very, very small. Okay, that can happen. So in such case, what happens? If you use sigmoid activation function, okay, with initially W being small, can imply that the output of sigmoid activation function, so essentially if we consider this as O1, O2, O3, and O4 as outputs, okay, O1 will be small, lesser than, sorry, O4 will be lesser than O3, its in turn lesser than, magnitudes of them will be even lesser than O2 and O1, because W is small and we are using sigmoid activation function. Okay, and then O4 and O3 may even tend to, O3 onwards tend to 0 itself, 0 values. Okay, and then they die down. Essentially what we are trying to say is the outputs die down over a set of layers. Okay, so but it is fine for, as I discussed, it's fine for small networks. For deeper networks, as we just discussed now, if we see the weight distribution, this is what is the histogram of weights. If we see the weights, say if we have actually at each layer, also 2 layer, if we have actually say 100 weights, okay, connecting them, here say another 100 weights, okay, here another 100 weights, connecting them. If we plot the histogram of 100 weights, then we can see that the initially weight distribution is fine with a variance of 0.01. Okay, later it may reduce to 0.001. Okay, and the distribution further 0.001 and so on. This is because W is multiplied for 3 times, 4 times, and so on in between. And sigmoid is anyway also is limiting its range from 0 to 1, right? So that's what effectively is happening here. So this is also not very good strategy. So we should have actually how small the W has to be. That we should get an idea on. Okay, for initialization, right? That's what is essentially being seen here. So at each of the layer, okay, the mean values are all shown here. Okay, mean values of weights and standard deviations are all shown here. So we'll take S into 0 value. Fine. So now we say on the other hand, if we initialize, if we keep the weights to be very large, then what happens? If we keep the weights to be large, okay, then what happens? Then W you are anyway multiplying with several times when we go along different layers, right? And then, so what happens? W3 into, if I assume that the things are somewhat closer to linear, or even if we write like this, W2, right? I just written for 3 layers. Okay, this is what is the output that we get as after 3-4 layers, right? So, and as you can see here, we are multiplying several times, and each is W is bigger, is large, imply that if we multiply several times, O is very large. And then they very large means, see, since we are using sigmoid activation function, so net values are large. Okay, not the O is large, but the net values are large. What is the net value here? This is the net value. This is net 1. Okay, and essentially this becomes the net 2, and so on. Okay, so net values are large, means that the sigmoid of net value will be close to what? Close to 1. That's what is being shown in the next slide. Whenever you consider that the values are, the weights are initialized with large values, 1 itself is large value. Okay, please note that. Because you have several weights, okay, each of the weight being multiplied with the input features. Okay, so weight value being 1 itself is large. Please make a note of it. Okay, and that what we see is the outputs all will be again this. And effectively, if the weights outputs are like this, okay, the learning also will be very poor, because there is no diversity in the output of the neurons, which is expected for learning better, right? So if there is a diversity, even the delta W's will be, delta O's will be different, and delta W's will be different. If there is no diversity, delta W's will also be same, and that will not help in learning, right? Please make a note of it. So these are good checks for you when you initialize and train a neural network. So this is a scenario where Xaiver, researcher who figured out how exactly the range of initialization of weight elements should be. This is exactly what we have discussed in the previous classes, which we directly used for initializing the weights. So how do we initialize? So we initialize if there is, say, D neurons here and NH neurons here, and there is, say, output O neurons here. Okay, if we have a network, okay, feed-forward network, then what's the rule with which we initialize the weights here? These weights are all Wj are initialized what? With a range of 1 by root D to 1 by minus 1 by root D to 1 by root D. Okay, and this can be uniformly initialized, random, initialized, either uniform or normal. Normal random variables. Okay, with mean 0 and variance 1 by root D. Standard deviation 1 by root D. Right? So this is essentially the fan-in. Fan-in is the number of input neurons, and fan-out is number of output neurons. Okay, so essentially we initialize based on the fan-in, number of input neurons. At this Wjk, how do we initialize? Wjk ranges from minus 1 by root nh to 1 by root nh. So this is the guiding principle that we have discussed in earlier classes, however given by Xaiver. So if you initialize like that, initially we may see that there is say good spread towards sending towards saturation, but as the layers move on, we see that the values will diminish. Okay, and then because we are using sigmoid activation function in all these discussions, and then subsequently we get, even after a reasonable number of layers, we get the reasonable distribution. But however, if we increase further the number of layers, still there is a difficulty. So we need to see in such case what we should do. Okay, so this works up to a certain number of layers, not too deeper. On the other hand, if we use Rayleigh activation function, the distribution will be like this, because Rayleigh activation function as you know, kills the negative values in the output. Okay, and you can see f of net on the output value that we see after activation function will only be there for positive net values. Okay, and hence they are also positive, purely positive. Even here they are positive, but it's at least you can see that if you use tan hyperbolic, they can spread from -1 to 1. If you use sigmoid, then you can see from 0 to 1, but the shape of this will be same, because at -infinity value of the weights, you can see that the height is the same. It will go to it will map to 0, right? So now for the Rayleigh activation function, if we see the output, this is only purely positive. And you can see that the as the number of layers increase, here also there is a W term that comes many times. Okay, so and hence the weights diminish, right? So if we initialize itself with small values, they will diminish. So with the Xaiver initialization, if we do initialization, yes, can be seen at different layers. The distribution of weights, okay, at that layer can be seen like this. So it indicates that Xaiver initialization is reasonably fine, but not fully appropriate for initializing when we in neural networks when we use Rayleigh activation function, right? So in such cases, what's the what modification do you suggest for this Xaiver initialization? Any idea on this? See, since the weights are diminishing after a set of layers, we wish to increase the strength of the weights. Then what? The diminishing factor will keep decreasing. Okay, and then it will be better. So what we do? Whatever we do Xaiver initialization, okay, to that we can multiply with 2 or slightly bigger number. In that way, we initialize W Xaiver into 2. If we do and initialize, okay, that will be more suitable for training the neural networks when we use Rayleigh activation function. That's usually is what is done. So the factor, multiplying factor can be anything, but a researcher by name, he et al., they have found that multiplying by a factor of 2, it will help to have the spread of the weight elements preserved over a reasonably long, deeper number of layers. Okay, what is encoding, and you can see that we multiply initially itself with say then the range is 2 by -2 by root nh to wjk 2 by root nh in a neural network where you have actually nh hidden neurons and d input neurons, okay, and c output neurons. Then the wjk are initialized in this way, and wij wji are initialized. What is the range with which do we initialize wji? They will be initialized -2 by root d to 2 by root d. Okay, this is there is an additional term of 2 here, which will enable us to preserve the weights even after reasonably more number of layers. And initially itself, the spread of the weights is more in the initial layers itself. Okay, and that's what you can see here. So let's see, there are other steps by which we can improve the learning of the neural networks. So far we have discussed about the role of input data, how the pre-processing should be done as input to the neural network, We have also seen how the activation functions, which activation functions are better. And further, we have seen how the initialization should be. Okay, now let us see some of the weight initialization should be. So given this taken care that initialization and pre-processing, the neural network architecture is also set. And there are few other steps which will enable us to train the neural networks better. One such very important thing is batch normalization. See, what happens usually, as we have seen before, is at each layer, the spread of neurons may be diminishing and varying dynamically. Okay, and if we define the range of inputs to each layer, that will help us to effectively learn better. In the sense that if we have a neural network, with the first layer, we are anyway what we are doing, input X is being demeaned or normalized. Okay, or we may even do the decorrelation or whatever. So we may effectively do pre-process the input features and give it. But this normalization will not be done at the subsequent layers, right? So currently what we are doing is, whatever is the output here, this is directly fed to the next layer. However, the way we position the input features, it is good to position the input features at every layer. That step is effectively done through batch normalization. So what we do in batch normalization is, so we start with the input being fed here. At any stage, if we have the input as xk, see what we usually do is, in training neural networks, as we said, we apply either stochastic gradient descent, giving only one sample xk as input, calculating its delta wk, okay, and then updating it for w or t plus 1, wk t plus 1 from wkt, right? This is stochastic gradient descent. The other one is batch gradient descent, where what we do is, we give all the samples x1 to xn, all samples together, calculate summation of all delta wk's, k varying from 1 to n samples, and update only once all w's, okay, wk. So this is not with respect to a sample. So this is all w. With respect to w, all samples, we update only w once. This is batch. And as we discussed before, it is very common to use mini batch gradient descent, in which we, instead of taking x1 to xn, we may take xn to xm. Okay, some say if this n equal to 1000 or 10,000, okay, we may be having m equal to 100, a small batch, but we would like to take the gradient updates with respect to the mini batch, rather than individual stochastically taking each sample or the whole batch together. In such case, what we do, we calculate k equal to 1 to m here, delta wk, and then use this for update of wt plus 1, right? So in this case, we have a set of samples at our hand to use them effectively for training. So each of the sample will be giving a particular output at a given layer, right? After sending through a layer. That we is even here assume that the input here is also xk for each of the sample. Now using each xk, that means xk is for a sample where k is sample index. Please note that x itself is a vector, so x1 to xt. Okay, so it may have several components, where actually this implies xk will also be a vector, x1, xk1 to xkd. For the case sample, we have d features or t features. and you have some such several samples, right? So what we usually do is we have now two axes, the two dimensions for the data. One is here d equal to 1, okay, d equal to t. So this is x1 2, so here x1 to xd, okay, and here 1 and sample m, okay, this is n samples, these samples, and here is dimensions, right? So batch normalization, what it effectively does is, since we have several samples at our hand, can we use them effectively, all samples, okay, and the spread of these samples, okay, at a particular given dimension d naught, okay, at given dimension d naught, can we standardize them? That means, see, each sample may be having some different values, okay, at a given dimension. So, but actually what the spread of samples say at a given d naught, okay, at given d naught, so we are fixing essentially x d naught, okay, and that samples, these are now considered over k equal to 1 to n samples. So the values may spread over, if we see this distribution, this may spread over what? This may spread over some mean, okay, mean and variance, right? Where the mean of samples, so mu is calculated as expectation of xk, calculated over k, okay, more samples. Please note that sigma square is again variance over samples for xk, right, in a given dimension d naught, okay, d naught is fixed, right? So, and using these mu, and these will be keep varying when we keep sending different batches, right? So first mini batch 1, okay, mini batch 2. So if we keep sending different batches, what will happen? Every time this is with respect to the batch, okay, batch 1, batch 2. So this mu and sigma, okay, mu 1 and sigma, okay, is keep varying, okay, for this keep varying, right? Because each of the time we are sending different samples, but can we, because we are essentially trying to learn from the same data, can we somehow normalize this over a batch and standardize them to say that every time we want to map this to a normal distribution of 1, 0, sigma square or 0, 1, okay, standard normal distribution. So what essentially we are doing now, we are trying to cater or combat the variation across different mini batches, okay. We want to consider each of the mini batch having the same variation while it goes to the next layer, that's all. But because overall it can vary because the samples are different, weights are different and so on. But when we move on to the next layer, can we bring in this xk initially being at this, say if we bring in a, here if we see xk over, say, distribution if we see over k, is essentially mu, sigma square. Can we map it through a batch normalization layer, okay, through some kind of normalization over this batch to 0, 1. If we do that, what's the advantage? Every time we are recentering the input to the layer before we send to the activation, then we send to the activation, okay, send to the activation in the range 0, 1 or in the linear range of activation function, and hence the information is effectively used. So now the batch normalization, how we do this is through a normalization. That is, if we have xk sample, what we do, we subtract the expectation and then divide by the variance for that dimension d naught. Okay, if we have only single dimension features, then it is x is simply whatever we have shown here. But if we have multi-dimensional features, then what we are doing is for a D naught, we are doing this. Okay. And this is simple procedure of batch normalization. This effectively what it does, we in addition to say at any layer, if we consider typically a layer, we are getting inputs here. Okay. So the input xk, okay, is sent through a batch normalization layer. Okay. So through this layer, what we are essentially doing, we are having exactly same thing xk hat. Okay. So xk hat, what is this xk hat? They are the difference between xk and xk hat is what? These are normal with mu comma sigma square. Okay. And these are normal with division 0 comma 1. This is necessarily be purely normal. Please make note of it. But we are essentially, since we are demeaning to 0, demeaning and bringing the mean to 0, and also making the variance normalization with variance, they effectively with unit variance. Okay. And after this, we may be able to, we will be sending with activation function. Okay, to get the output. So the let it be sigmoid activation function or whatever. And this whole thing is at a layer. Okay, so whatever we had here, summation multiplied by sigmoid. This is now if we write in this form, summation first. Okay, after that we have batch normalization. Okay, and then sigmoid. Okay, this essentially is broken into 3 steps now. Okay, in between the net values that we get, okay, and then the activation function, we have introduced a batch normalization, so that to the activation we send these samples in a known range. Hope this is clear. As you can see here, we do at a given D naught, okay, use the whole batch of samples and say so x1 to n samples or xm samples, and perform batch normalization. Okay, and here the variance may be different. Okay, and here the variance may be, so mu here may be different, mu here may be different, and so on. But after batch normalization, if we see this, each of them are with 0 comma 1. Okay, each of the batch here, each of the samples here, if in any dimension, if we see, they are spread over 0 and normal 0 1. That's the advantage, right? And neural network now can be seen in this way, where after fully connected layer, we introduce a new layer called batch normalization layer. Subsequently, we apply activation function. Okay, and then followed by fully connected layer and batch normalization and activation function. Okay, so in between each of the fully connected layer and activation functions, we have a batch normalization layer now. Fine. This is done both in fully connected networks as well as in convolution neural networks. And the other advantage or other version of batch normalization is, see, why should we map through batch normalization layer? After this fully connected layer and batch normalization layer. So as we said, we map it to n0 comma 1 here. This may be say n, so each dimension if you see, so we are telling about each dimension here. Okay, it can be mu comma sigma square. Okay, so why should we have always to 0 comma 1? Can we map this to a known mean and variance? The answer is, say, mean of beta k and variance of gamma k. Okay, the answer is yes. So now what we do is, so we first demean it. Okay, after we demean it, so we already initially have xk's. From xk, demeaning means xk minus expectation of over xk, expectation taken over k. Please note that, because we are doing over all samples of mini batch, not over dimensions. Okay, xk also has dimensions, and root of variance again over k samples of xk, right? And you have actually, this is xk hat. This is the batch normalization. Okay, with you mapping to unit Gaussian. Now what we want to do, we may not be happy with this because sometimes the mean zero and unit variance is not very suitable. We would like to have a beta k and gamma k as the guiding parameters for the distribution. In such case, what we do, x hat double hat k is essentially what is a transformed version of x hat k. How do we transform it? X hat k into what? Gamma k, because the variance term come here, or the gamma square is variance, then gamma k will come here. Okay, and then where does the beta come? Plus beta k. Okay, so this essentially transforms this normal distribution 0, 1 to beta k, gamma k. For a particular sample, we are doing this. Okay. And these beta parameters can also be learned, okay, for each batch or for the whole batch. So this is while training. While testing, what do? We remember these gamma beta parameters, okay, or we remember the means. Okay, we also remember the mean and variances. Okay, but because for the test sample we don't have mini batch. Okay, so for over each mini batch we have actually some mean and variances. So expectation of k over xk, this is say for a batch 1 it will be mu1. Okay, for batch 2 it will be mu2. Okay, and so on. For batch 10th batch it may be mu10. So these overall mean also we can calculate, or we can standardize to one of the batch mean, and that mean we remember, and overall variance also we remember. Okay, overall batches, those things those aspects will use while testing. Okay, so while testing, since we applied batch normalization in training, the batch normalization layer is also needed in testing, but however the parameters we use are from the training. Okay, so whichever we use during training, we average them over all mini batches and use them. This is how we use, and gamma beta also can be the average versions. So this batch normalization layer is known to be very very important and well. Several reasons. One, every time at each layer, it reinitializes the range and brings the range to a linear range or a workable range for the activation functions. So it acts as it helps in setting the learning parameters higher because you are in learning range. And it also reduces the effect on initialization because you are respreading the data every time. So we if something like the input data and the initialization are not very appropriate, with respect to the initialized weights, input data is not appropriate. We are anyway reinitializing the input now, or reprocessing the input, and hence that will reduces the effect on initialization of the weights. And it also acts as a regularization. Every time we are jittering the data into slightly different space or different range and trying to learn the parameters of the weight parameters for classification. So we will discuss the rest of the things in the next class. Thank you.